So, here in this lecture session, we will be considering a topic where truth table is to will be mapped to another domain where it will be called as Karnaugh Map for mapping the truth table to implement digital circuits using basic gates which are you can consider OR and NOT or even NAND, NOR like this. So, in this truth table, whatever you have learned about of a basic OR gate, AND gate or other known gates there, not only that, if you want to go for another logic systems there to devise which may not follow your known OR, AND or NAND, this kind of operations there, but still you can proceed for it. But only thing is that if you are implementing something there, up to what extent you can minimize the number of gates which will be used to implement that logic circuit. That is the aim here. Now, for that, this kind of approach is very much useful, where Karnaugh Map is nothing but a map only, which has come as name has come as Karnaugh Map from the name of the person there. So, basically it is a mapping. So, in this lecture, our aim will be to learn how to map, what is the utility of that map, which way we will be efficiently using that map, to learn the procedure for that. But in addition to that, I will request you, please be alert there when I speak about the procedure there, along with which I will be speaking about the logic behind or the idea behind or the philosophy behind or the procedure what we are following there, why we are doing this. Is not there any other way to do? So, those things should be there always in your mind at the background. We will proceed in this fashion. Okay. So, let us start with our one truth table. Say we consider in this fashion. Two variables are there at the input A and B, which have the logic out Y, say. Now, if I am saying two variables are there A and B, A can be sometimes 0, B can be 0, 0, 1, 1, 0 and 1, 1. These are the combinations which can appear there in the system. Since two variables are there, only 4 combinations are there for this. Now, Y is the function which will be defined as per our desire. Like as we were considering for OR gate, it was 0, 1, 1, 1. Now, let me take differently 0, 0, 1, 1. Is there any well known gate for this? But it is possible to design where Y is defined in this fashion, where the inputs will be A and B there. So, I can say Y is a function of two variables A and B. So, Y should be defined in terms of A and B. Now, if I want to define this logic here or the logic gate to derive, in that case I can say there that I find from this truth table that output Y will be 1 if A and B bar or A and B are 1. Simple understanding goes like this. So, I can easily write one expression for this Y, which is given here, which is a function of A and B. In terms of A and B, I can write it as A B bar or A B. Anything? Okay. So, in last class we considered A B bar B. That was an exclusive OR gate. It is not that also. It says that if this two, this is 1, this is 0, then only 1, and it is 1, then only it is 1. But simultaneously 2, 1 are there. So, I could write this expression, either this one or this one, output will be always 1 there. Okay. Now, if I implement this, what do I need? One AND gate for this, another AND gate for this, then finally I will take those outputs to the OR gate so that I can implement the Y there, the digital circuit which will be having the output Y. Okay. So, now this kind of things, if I have many variables here at the input, y is a function of n number of variables there. So, this y will this combination also will be many, and this y also will have many terms there. There will be function of the input variables there. In that case, I may need to simplify the circuit in such a way that it needs a minimum number of gates there. So, for that, this is the beginning, that which way we will tackle those things there. So, let me first introduce what is Karnaugh map basically. Okay. So, let us take this Karnaugh map is for the two inputs A and B for a particular output there. Now, let me map it in this fashion. A bar A is written this way and B bar B, because I have two possibilities, either if A is 1, then another will be 0 of it. If B is 1, then another one will be 0 of it. Now, we consider that, say A 1, in that case A bar is 0 and B if it is 1, then another is a 0 there. Okay. Now, this is written purposefully like this, because now I want to take the combination between them. If I say A bar B bar, it can come sometime here for any output I am talking about. Okay. So, now let us name this A bar B bar as M0. Why the 0 is? Because I am saying it is 0 and 0. So, 0 0, that means this one, means this 0 0 I am talking about. Let us name it, I am just asking to name it. Okay. So, this is an A B bar is M0, and then A bar B, A bar B, A bar is A is 0 and B is 1. So, it is M1, then A B bar, it is M2, and AB is equals to M3. Okay. Why I took this? Because A bar B bar, A bar B, A B bar A B. These are the things I have considered there. Okay. So, now this M is purposefully taken here as M, because this is called mean term, because all these are called mean terms. So, mean term 0, 1, 2 and 3 there. Okay. Now, if I want to locate these locations here in this map, which are related to A and B, which are actually part of our truth table, we will be coming to that at the end. Okay. Now, if I ask you M0, where is the 0th position then in this map? This one? 0, 1. What is the 1? Here? 1, 0. And this is 3. So, min term 0 means this one, min term 1 means this one, min term 2 and 3 like this. For two variables, because shortly we are going to extend it for 3 and 4 successively. Okay. Now, if these are the terms where mean terms are found as product of two variables there, it is to be noticed. These mean terms are nothing but product of two variables which are there. Maybe some is complemented for a particular mean term and another is not, or both are complemented, or nothing is, or nobody is complemented, like that. But it is a product of those input variables. Fine. Now, if I want to relate this one with this, which way I will go? If I want to know that this expression in terms of this mean terms, then can you tell me A B bar, what is it there? A B bar, it is 2. So, it is M2. What is this one? Or M3. I can write this way, okay, or I can write here like this, where m is 2, 3. This is the notation. That means I have to take sum of those products which are there at 2 and 3 location of this map. This is the meaning. So, this kind of representation will be called sum of products or SOP. Okay. Now, if this sum of this product, those things are now identified here, I do not like to always visit this one and then come here, not this way always. I will be looking into the desired logic circuit logic output here, and I will map it to the Karnaugh map, and I will be proceeding further. And finally, I will be writing down the final expression of this y. This is the procedure. Okay. So, now to make that, you will be making a Karnaugh map B bar B, this one, and in it you have to find if this is the device to be implemented. For that, who are the min terms? They are at level high. If I want to name the min terms here 0, 1, 2 and 3. Now, let me find where are the ones. Here is 1 at 2. So, I will be putting here at the location 2, 1. Similarly, if at 3 it is 1, then at location 3 I will be putting 1. What is about the others? It is found here, it is 0. So, put it 0. So, now this truth table is mapped here in the Karnaugh map. Okay. Now, if this truth table is not there with you, but the Karnaugh map is there, means it is everything is set to you. How? If I ask you to write the expression for an output y, you will be seeing that where the ones are there. That means A B bar plus A B, just like this one, straightforward. But in this Karnaugh map has the advantage that you can group them together, so that you can minimize the number of terms which will be involved in this y, or in other way I will say number of gates which will be required less there, or it will be minimized. Okay. So, that way let me consider these two together as a group. If I group this together and look into this truth table, I can see here if A is 1, then this exists. It does not matter whether B is 1 or 0. Okay. Because this is 1, if A is 1, does not matter whether B bar or B, that is B is at 0 or 1, because both the locations have the 1 there. In that case, I will say this expression is just y is equals to A there, because I have come here and I am seeing these two are complemented to one another. So, finally, it is A. Does it say the same thing what we learned in the last class? If you proceed with the mathematics what we derived there, please take one common of A there, B bar plus B, B bar plus B is again 1. So, it is 1. So, it is proved. Okay. It is there. So, but the procedure what it is, that is to be learned here actually. That I will go here and I will see for which the complements are present there to one another, and I will be just discarding that part. Okay. This is the fundamental of Karnaugh map. Now, let us implement the same logic device which we took in the last class as y, A bar, B bar, C bar of like this big, on big expression there, and finally, we saw there that is nothing but C complement. Let us take that one. say we have now not 2 variable, but 3 variable which will be considered for representing this function in some term, where these are the 3 input variables which will have how many combinations? 8 combinations. Please write down those. Fine. Now, in this, with this combination, I have to devise one, I have to implement one logic device there where y should have a particular expression which is provided by somebody or you are planning to. Let us take that expression what we took in the last class. A bar, B bar, C bar, then A bar, B, C bar, A, B, C bar, A, B bar, C bar, A, B, C bar. I think this was the expression for this particular y. Okay. Now, if I ask you this to implement in the Karnaugh map, who will be existing there? That's you need to find out there. Okay. Now, please define this y from here. Can you? It is found there. These individual mean terms, which are the product terms, they are odd with one another. So, any one, if it is 1, then output will be 1. Say A bar, B bar, C bar. Who is that? A bar, B bar, C bar. So, this might be 1. Then A bar, B, C bar. A bar, B, C bar, 1. Then another one, A, B bar, C bar. A, B bar, C bar. Then A, B, C bar. Okay. What is about the others? They are all 0. So, now if y is said, means it is asked that you do some combination of A, B and C in such a way that output y becomes for these conditions. Okay. Now, let me put this in the Karnaugh map there, where one Karnaugh map will be there of 3 variables. If 3 variables are there, take this A, B, A bar, B bar, A bar, B, then A, B, then A, B bar. Fine. Then C bar and C, only 2 are there. This should be the Karnaugh map. Maybe one small question can come there. It is fine. A bar, B bar, C bar, you have put there A bar, B bar, and A bar, B, C bar, you have put there. But why this A, B has come in between? Other way, it has a specific reason actually. After we go towards the end, you will able to see why I have made it. It is purposefully to make the Karnaugh map efficient, to make it minimize the logic expressions which will be asked there to implement at the end. Okay. So, we will follow this thing. Now, in this, if I ask you, please name the mean terms. Who is 0? 0, 1, 1 here. Is it 2? 2, 3. Is it 4? 1, 1, 0. Is it 4? Never. 1, 0, 0. That is 4. Okay. 1, 0, 1. That is 5. Now, 1, 1, 0. 6, then 7. These are the mean term positions in the Karnaugh map of 3 variable. Fine. Now, if I want to place my truth table in this Karnaugh map, I like to use the mean terms which are here as 1 to place 1 in the Karnaugh map in this. So, let me find out who are the mean terms there present. 0, 1, 2, 3, 4, 5, 6 and 7. Now, what is to be put 0, what is to be put 1 there? Position 0 is at 1. So, put it 1. Position 2, no, position 0 is at 1, yes, position 1, 0. Then position 2, 1. Position 2 is 1, 3 is 0, 4 is 1, 5 is 0, then 6 is 1, this is 0. This is mapped, this truth table is given there, now it is mapped to the K map, which is for some purpose we have used here. Okay. So, now if the same idea I put here, I will be looking for those ones and their presentation, which way they have taken their positions in the Karnaugh map. See here, if it is C bar, it does not matter whatever the combination of A and B is, because all are present here. So, the output can be written as C bar, which you did in the last class for minimizing this by taking C bar common and like that. Okay. So, this can be directly put from the observation in this fashion, but Karnaugh map says like this, you follow the procedure because you are getting prepared for bigger map actually. Okay. For that, what you will do, you group them in terms of 2 power of something, means 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, like that elements. So, here earlier we took group of 2, here also I can take group of 2. If I take group of this 2, then the logic would be from here 1 would be getting cancelled, like one is B bar and B which are present there. So, I had to leave them and only A bar was common. So, A bar, C bar I had to write. Similarly, for this A is common, B bar is not there. So, A, C bar I could write. Just like A bar, C bar or A, C bar I could write. But if I have scope to make bigger group, which is now 4 here, 2 to the power of 2, that is also allowed. If you take this group, now you consider nothing to consider here because all the combinations are gone, only C bar is present, that is why you could write this way. Now, if you ask the proof, then you can take common from here the C bar part and A bar plus A would be there, A bar plus A means 1. So, it is again C bar. So, now the idea should come from here that if I could write this way or I could write this way, but this I am finding efficient one, which way it could happen. What is the reason behind? Reason is that you will try to make the group in such a way that all the ones are grouped and the group should be as big as possible. The more the size of the group there, the term will be minimum and minimum there. This is your target. Okay? So, with that logic, it is like this. But if you say which way people could think like this, how it can come? In that case, I will say no need to go for that also. You can come directly from here. If you have another way of looking into the things, like, see, if you look into this truth table, here you are seeing that here it is 1, here it is 1, here it is 1, here it is 1. For others it is 0. But here this is 1 if C is 0. Here also it is 1 if C is 0. That means whenever C bar it is present there, output is becoming 0. With that also you can put the logic output Y as C bar. But how far you will able to do if the number of variables are more there. So, for that this Karnaugh map is so popular and useful. Okay. Let us proceed for 4 variable Karnaugh map. Here I am saying it is a 4 variable Karnaugh map. That means I am basically talking about 4 variables with some output y. It is like this. Now, if I ask you to make the combinations there to complete, I think you will complete the things like this. This way you will continue and you will give the min terms as 0, 1, 2, 3 this way. Fine. Now, some y will be there, that will be decided later, but these are the variables there present. So, let me first find the K map for 4 variables. For this column, 2 variables are already considered there. Follow the same. A bar, B bar, A bar, B, A, B, A, B bar. Follow the same technique for the other side also. C bar, D bar, another variable has come there. Then C bar, D, then C, D, C, D bar. It is done. Okay. Now, if I ask you to locate the position for min terms, you will write 0 here, 1, where is 2? At the right side, because 0, 0, 1, 0. If it is 0, 0, 1, 1, then it is 3. Okay. Similarly, if it is then 1, 0, 1, 0, 0 means, so it is 4, 5, 6, 7. Okay. Then where I will get 8, 0, 1, 0, 0, 0. This is 8, so it is 8. Okay. 8, 9, 10, 11. Okay. Then 12, 13, 14, 15. Done. 4 variables, 16 possibilities, 0 to 15. Okay. Now, say in this Karnaugh map, one Karnaugh map is given to you with the logic output which is desired there as this fashion. Just let me take this first. This is the map in which the min terms which are given here in this y, that is to be located. Okay. So, for that, say they have given one expression like this, y as summation of the min terms of something, or in other way I will say, let me fill up this first, then come to that, because we have already seen this way transition. Let me take this Karnaugh map. 1, all 0, 1. So, this is the Karnaugh map given to me. Do I need any other from this now? Because for this they are saying one y is required. For that y, logic is already given here in the Karnaugh map. If I want to fill up, I will fill up later. But if I ask you, if it is given there and y expression is to be found out in terms of mean terms, which will be as a sum will be coming to the y, where mean terms are the product terms, they will be summed together so that I get the output. So, this summation has come there, and mean terms who are involved in that summation, let us find out. Who are they? This position, who are they? 0, 1. Then why not 2? I think this position is there, 2. Then 4, 5. Then 6. Then 8, 9. Then 10, 12, 13. 12 and 13. Position of this from here, I have put it down there, where the mean terms are found in this fashion here. If I want to locate them here 1, where I will put 1? Here, 1, 2, then at 4 like this, because this is 0, 0th position is this one, this is 1, 1th position is this one. So, actually truth table were given like this. For that I found the mean terms this way, and for that I put them in the map, or the map is given this way, I have got the mean terms like this. So, I can say that y is this way, where this term is 0. Any way you can go. Okay. So, now if this is the map given to me, and for that they are asking if these are the ones present in this Karnaugh map, what is the simplified version of that y expression? Okay. Let us proceed one by one. Expression for y without doing any simplification in it. If I want to put, what should I write? Straightforward, without doing anything to it. Straightforward, I will be seeing where the ones are present, and if this one I am trying to take, then A bar, B bar, C bar, D bar, or this term A bar, B bar, C bar, D, or no need to take, go here A bar, B bar, C, D bar, then here A bar, B, C bar, D bar. Continue. How many terms will come? I am finding here 8, 9, 10, 11. So, 11 or 11 and terms will be available there, and of whom ORing is to be done there. And in between, while doing ANDing, you need 4 input AND gates for all. Is not it? Now, let us go for another implementation. Implementation 2 of same y. Output will be same. For that, we will take the idea of grouping. So, let us start with 2 groups, 2 as a group. I can take one group like this, another group this way, third group, fourth group. Fine. Now, say here if it would be here 1, then I could group it, but I could not, because it is 0, 0 like this. So, let me put it separately like this at the beginning. This is also possible. Your idea should go there. Why it is possible? Because that one is there, I will be directly writing the expression for it, then things are incorporated. I am not avoiding anybody. if it is there alone in it, so my expression will come something there, which way, let us see. Say for this group, what should be the expression? I am seeing here in this d bar and d is complement to one another. So, C bar is fixed. So, A bar, B bar, C bar. For these two, which I wrote here two expressions, now that they have gone to this single one. So, input has become only 3 input NAND gate now is required, or I have to visit this place also. Let me take the groups first and then I will come to them. I will take this one, then that is A bar B C bar plus A B C bar plus A B bar C bar. For this 4 are for this 4 groups. Now, go for the remaining. What should be the expression for this? A bar B bar, just like earlier, C D bar. For this, A bar B C D bar plus this one, A B bar. Done. Now, how many terms are now there? Here 4, 5, 6, 7, which was earlier 11. Okay. Now, I said you that you can make a bigger group also. So, let me take another implementation, which is implementation 3, say, of same Y. In this, I will extend the group in this fashion. This 4 and this 4. Okay. And since they are this way, I can take this also as a group, but I do not have any scope for this one. So, let it be there. So, at least this 4 are one, this 4 are another group, 2, group 3, and fourth one is alone. So, how many terms are now? Only 4 terms should come, which was 7 earlier. Let us go for that. If I go for this first group, I am saying here it is B bar complemented, so A bar is left. Here I am saying D bar is complemented, so C bar is left. So, this should be written A bar C bar. Done. Okay. Similarly, for this one, A C bar, 2 terms are found. Now, for this, A bar C D bar. Now, final one will be as it was, like this, because nothing is done with it. Okay. Now, if you have scope to go further, like these are the group of 4 and this is the group of 4, it is present, why not to make the group like this, where 8 will be present? Okay. Let us make that group as 8. Implementation 4 of same Y. If this is the group, then tell me what is the combination of A and B? All are there. So, no need to take any effect of A and B, because complement of all are there. So, only thing is here. So, only put it C bar. For this group, what is about other? Another term will come like this. This quantity will come here. What it was? Oh, I did not write this expression. This expression I did not write there. A B bar C D bar. It was there. Huh? No, I have written. Okay, sorry. It is there. Now, so in this, these were the 2 quantities which were there for this group. This and this, which was separate. One, this came for this 4 and this came for this 4. Now, I will speak about rolling. Please take one important note here as rolling. which is another advantage of Karnaugh map. And here you will see why I have mentioned this A bar, B bar, A bar, B, A, B, A, B bar, this in this fashion. See here, grouping is possible from this to this also. How? Just consider this two and consider this two. If you can make this two as a group which are side by side, or if here would be there, then you would be making group of this 8. That if it is possible, and that same thing I am saying here it is possible like this to make the group. What does it mean? It means on this paper you have put this is a Karnaugh map. In this paper, few elements are there in this edge, few are there in this edge. Now how they relate to one another? They are again made complementary to one another so that it maintains this sequence the way you have put there. So it is just like rolling this paper like this, which will be looking like a cylinder or a pipe. So this has again come side by side to this column there. So if it is so, as if it is here, so you are making them as a group. Okay. So this is the reason behind that. These two have gone other side of this one, and it has completed the group this way. Notation is this way, presentation is this way only. It has gone, it has come. Now if it is so, then what is the logic for this group? Here B bar is gone, only A bar is there, and for this and this, C bar and C is gone, only D bar is present. Is not it? C bar, C, but D bar is common for both. So C bar is only, C is only complemented to the other. So you could write only A bar, D bar. Here, is it possible to group with the idea of rolling? If this is just side by side of this column, if it is presented this one, then this one has come to this one. So make another group like this. There one, another one is this side. Okay. So now if you present this group, then what would be? In this I am saying A, P bar is there, and C bar and C is there. So it is D bar. Okay. Any problem in rolling? Nothing. Okay. Let's extend it further. Okay. So if I make the same group like earlier, this one is bigger one, and this is there, and this, and this as 4. What happens? 4 corners of this, they are also of same kind. Like earlier I said it was cylinder, 2 edges were connected there. Now what is about the other side? If you make roll, then they are also coming close to one another. So in that case, you will have this way also that rolling possible, or other way you can say, earlier you said about the rolling in this side, what is about this side to roll? That is also allowed to you. Okay. So if it is so, then this one and this one can be grouped, this one and this one can be grouped. If it is so, why not these 4 which are at the corner? That can also be grouped. Okay. So this way, how many times will be going for this kind of grouping, or which way I will know that this is the best way of grouping? That is also a problem. That's why I said you try to make the group as big as possible and try to make the number of groups as less as possible. And in doing so, if you find that the ones which you are using there for making group, that has gone to some another group already, nobody is left there. In that case, no need to take that, because it is already considered somewhere. Just like in this group, if I take these two are left, or if I take this group also, then also these two are left. So, you cannot avoid this grouping. But if it would be coming to other place, then I could make the group of this 4 and other way. Only thing is that I have to visit all the high states which are present in the Karnaugh map. Okay? So, that way if I group them also, what is the expression here and here? A bar A gone, A bar and A is gone, so only B bar will be present. Similarly, here and here C bar C, so only D bar. So, for that the expression will become B bar D bar, D bar for this consideration. These 4 are taken. Now, for this and this, what it was? A B bar D bar. For this and this and this, what was the expression? I could get an expression up to this level. You please check this. I could simplify this Karnaugh map with this idea, up to this idea, whatever I have spoken, I could get this many combinations there to get the final expression of y like this. If you can, A bar, but I could make further simplification actually. Oh, sorry. A bar, sorry, A bar D bar, right. A bar D bar. Okay. Let me proceed to the another. Please check it, this one is coming or not. Okay. Here another concept I will put here, where this kind of condition come there, which is called don't care condition. Here, if the Karnaugh map is given to you like this, in which these are the places about which it is said nothing. Okay. It means it does not matter whether you put 0 there or 1 there, it hardly matters to it. Those conditions are called don't care condition, and in that we use the notation like this, where 0 is don't care, which can be taken 0 or 1, anything. Is there any utility of it? Yes, it is. Say you are considering x is 0, this cross is 0. So, this is 0, this is 0, this is 0 like this. So, what will be the expression for y here? Is there anybody to group? This one, A, B bar, C bar, D. For don't care condition is 0, if you consider this cross as 0. But if I ask you, please consider that x 1. If these are considered 1, then this is 1, then you can make a group like this. It's possible? Or you can make a group like this. Possible or not? So, beyond that, is it possible? You cannot take for 6. 0 is here actually. So, take this as its condition for 1, 1, 1 here, and find the expression as how much it is? A and D for x equals to 1. So, that way if it is useful for you as 1, use it 1, if it is useful as 0, use it as 0 there. Fine. Now, one question should come to you, like here whatever you have spoken for this 1 hour, it is only for the ones. What is about the zeros, what it were there in this? If I would like to write the expression for those zeros, then what happens? In that case, what you will do, the expression here it was given in terms of the mean terms, means this ones there. Like for this expression, if the mean term is only at this place, what is the number here? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So, only 9 was there. But since don't cares are there, that may give you some another expression there. But if only mean term is 9 and max term is also defined like this, that also should be possible to express. Okay. So, to make that, let us take one example with not only don't care, but some expression, constructive expression actually. I will be little bit first. Let me take this example where y is with product of sum, what it is? I found m of 1, 2, 0, 1, 2. Please tell me 0, 1, 2, 3. 0, 1, 2, 3, 4, 5, 6, 6 and 7. Then 8, 9, 10, 11, 12, 13, 14. These are the min terms. But if you want to consider these zeros there for expressing this y, you can go in other way also, where you will be talking about max terms. Who are they other than this? Means these locations. Who are they then? 1, 0, 1, 2, because 3 is found there, but 0, 1, 2 is at 0. Similarly, 6, 7 is there, 4, 5, then 8, 9, 10, 11, 12, 13 and 15. Say don't cares are considered 0. So, these are the max terms. Now, in this sum will change to product. What does it mean? It means here you wrote the expressions as A and A, B, C, D plus A, B, C, D bar plus like this. But here in this you will be writing those as not as a OR of AND terms, but AND of OR terms. Means you will be multiplying after summing. So, product will be taken after the sum. This is only the difference. Okay. So, now if I ask you to write the expression for this logic where this grouping is allowed here as 0, 0 which are here and these two are here, you should be able to write the expression with this 0 as a consideration. Now, if you write what the expression for this, I am seeing here B bar is gone, A bar is there, write A, not A bar, write A. Okay. Similarly, here C bar is there, so write C, but with OR, not AND. This is the difference, like this. Similarly, for this, now it will be AND. Earlier it was or, now it will be and. Of this, who are they? For this two, B bar is common, A bar is not there. So, it is B plus C bar plus D, done. Okay. Now, if you consider this do not care as 0, then why not to take this group? It is allowed. If you take this, then nothing to consider here, only C and this remaining part, or you take this and this, this and this 4. What it is? P bar means B and there D. Am I right? This way. Now the question should come, how I could do this? Here earlier I was using AND gate first, then I was making ORing of them. Now I am making ORing first, then I am making AND. Then I will give you a small reach to you, like what we discussed in the last class, De Morgan's theorem. What it was basically? It was A, B bar if it is A bar, B bar, or A, B bar if it would be A bar or B bar. Now you match your things here, what it is basically. If you are talking about not of that expression what you were using earlier, because earlier we were considering 1, now you are considering 0. So it is just not of it. If it is not, obviously it has to come in AND form. If it is or if it is in AND form, if you take not of it, obviously it should come OR form. This is the fundamental thing of it actually. It had to come. Okay. So this way I will request you, please with this idea, you also try for different combinations and try to develop yourself for that, so that you do not hesitate to make them extension for other things also, other possibilities also there. Because in between the reasons or logic behind is already discussed in this class. Okay. Thank you for today.